Welcome back, everybody, to the next video. Took a weekend off here. We're getting back at it with Hecke eigenforms today. So let's go over the definition and some facts. So a Hecke eigenform is a non-zero element of Sk n chi for some Dirichlet character chi mod n, which is an eigenvector for the operators Tp for all primes p simultaneously. So we're looking at maybe a non-zero element f, let's say, such that Tpf is lambda pf for some constants lambda p, which will be called the eigenvalues associated with f, and f itself will be an eigenvector. If f is the sum over n at least one of a of n q to the n is such an eigenform with eigenvalues, let's say lambda sub p, then the formula for the Fourier expansion of Tpf from the last video tells us that we have the following recursion relationship. So we have a of pn minus lambda p a of n plus chi of p times p to the k minus 1 times a of n over p equals 0 for all natural numbers n. And what you should do is, if p doesn't divide n here, a of n over p is just to be interpreted as 0. Okay. If you set n equals 1 here, what you find is that a of p is lambda of p times a of 1, which means that if a of 1 was 0, then a of p would be 0 for all primes p, which by induction on the number of prime factors of n, take n and prime factorize it, this actually shows that a of n would be 0 for all n. Well, if a of n is 0 for all n, the a of n are the Fourier coefficients of f. That would mean f is 0, but f is supposed to be non-zero, so that's kind of a contradiction. That leads to the following observation. We'll call this proposition 10. If f is the sum over n at least 1 of a of n q to the n, and it's a Hecke eigenform, then a of 1, its first term, is non-zero. Okay? And so this motivates the following definition. A Hecke eigenform f, given by the usual Fourier expansion, is normalized if a of 1 is 1. So if the first term is not only non-zero but 1, we'll call the form normalized. And so what this proposition says is, if you give me a Hecke eigenform, there is an appropriate scalar I can multiply it by to normalize it, to make its first coefficient 1. Okay? Now, if I have a normalized eigenform f, the relationship above, the a of pn minus lambda p a of n plus chi of p p to the k minus 1 a of n over p equals 0 for all n, says that lambda p equals a of p, right? In fact, it'd probably be better for me to just reference this equation right here. Lambda p is a of p because a of 1 is 1, right? So if you use this fact and induction on prime powers combined with the above relation, this is an exercise you should try, you see that a of p to the v m equals a of p to the v a of m, as long as m and p are co-prime. So in other words, as long as m and p are co-prime, the coefficient function is multiplicative, okay, on m and p. If you induct again on the number of prime factors of an integer L, such that the GCD of L and M is 1, you find that a of Lm is a of L, a of M for all L and M and N, as long as the GCD of L and N is 1. So what this is saying is that Fourier coefficients of Hecke eigenforms are multiplicative on co-prime indices. Okay? So, or in other words, the map that sends n to a of n is multiplicative on, well, it's multiplicative on co-prime inputs. Okay? And so what this tells you is, much like the Riemann zeta function has an Euler product, you can say the following. The sum over n at least 1 of a of n to the negative s, so the Dirichlet series associated to f, actually equals the product over primes p of the sum over v at least 0 of a of p to the v times p to the negative vs. This is an easy check given the fact that this function is multiplicative, so I'll let you do that as an exercise. In other words, I mean, this is a question that we've had long-standing for several videos now. Dirichlet series associated to certain cusp forms f, namely the Hecke eigenforms, do have Euler products, and so we can call this sum here an L function or an L series associated to f. Okay, and actually we can do better than this. So proposition 11, let's let f of z be given by the usual Fourier expansion, and let's let it be in Sk of n chi. The following are equivalent. F is a normalized Hecke eigenform, and there is an Euler product like this. And in fact, I can tell you what this Euler product is more specifically. It's the product over primes p of 1 minus a of p to the negative s plus chi of p times p to the k minus 1 minus 2s power, and then take the reciprocal of all that. Okay, so proof of this, one direction is just evaluating this internal sum formally, which can be done with kind of standard power series arguments. and using the recursion formula up here. Okay. And the other direction is actually just reversing the argument that we gave here. Okay, so I would see DS chapter 5 and CSS chapter 3 for more information on this, but actually having an Euler product characterizes being a normalized Hecke eigenform, which is a little bit surprising. Okay, and so let's tie up a loose end now to end the video. If F is a normalized Hecke eigenform, we can now call its Dirichlet series sum over n at least 1, a of n to the negative s, the L function of F, and we'll denote it L of Fs. That's again because not only does this series make sense and converge on a right half plane, but it actually has an Euler product. Okay. There's one remaining issue though. So one remaining issue is we know from proposition 9 that there's a functional equation relating L of Fs, so this, to the Dirichlet series associated to the modular form F bar sub k Wn, where Wn was the negative 1 over nz matrix. The problem is we don't actually feel justified calling the Dirichlet series associated to this guy an L function yet, because we don't know it has an Euler product. And so it remains to figure out conditions under which both F and F bar sub k Wn are Hecke eigenforms. Because remember, being a Hecke eigenform is what characterizes your Dirichlet series having an Euler product and hence being an L function. Okay. And so this leads to the theory of new forms, which are very important objects we've been discussing since the beginning of this series. So we'll start talking about those next video. So thanks for watching, and I'll see you then.